Right now it's time to look at the integrated rate law for a second order reaction. So just like the first order of the reaction, the goal here is to get a linearized line so that we can make predictions about a reaction based upon time and concentrations. So a second order reaction is one where we have a particular reactant that has a doubling effect on the rate. So if we double the concentration, we quadruple the reaction rate. And so just like last time, rate is equal to either change in concentration over time or the rate constant times the concentration, but this time it's squared. So this equation looks different than the first order reaction because it's a different type of reaction. And in this case, we have 1 over the concentration minus 1 over the concentration at time and initially, and that's equal to the rate constant times time. So unlike the first order reaction that used the natural log, this one just uses the inverse, or 1 over. And again, this equation right here is given to you on the AP sheet, but it is not labeled as the second order rate law. You need to instead remember which one's the first order, which one is the second order. Just like last time, we can linearize this equation by setting it up in the y equals mx plus b format, where we take our our inverse of concentration versus time, and then range it like this. Once again, k is our slope, time is our x-axis, and our intercept is the initial concentration. When we do that, we get a nice straight line. This time it goes upwards though, so it is a positive slope, which is why k is directly equal to the slope. So we don't need to multiply this one by -1. Now we can recognize a second order reaction just like we can recognize a first order reaction. Second order reaction, 1 over the concentration versus time, concentration at time versus time, gives us a straight upward slope like this. If we were to do this with a zero order reaction or a first order reaction, we would not get a straight line with the inverse of concentration. So here's a good example of a question. So using our data provided, we've got our nitrogen dioxide decomposing into nitrous oxide and oxygen again, and we would look at our two graphs right here. So this one is the inverse of the concentration versus time. This one is the natural log of concentration versus time. And then over this side, we have our data that we gathered. Notice how this is concentration versus time. If we were just to plot that, we would get a curved line. But when we take the inverse of those values and plot them, and when we take the natural log of those values and plot them, we get two different graphs. So the first part wants us to find the rate law. So rate law is rate is equal to rate constant times the concentration of, in this case, it's going to be NO2, raised to a particular power that marks its order. So to figure out the order of the reaction, we don't need to look at rate data and do the whole derived thing. Instead, we can just look at our graphs down here. So this one right here gives us a straight line. That one gives us a curved line. If we get a straight line plot on a 1 over NO2, that means it is a second order reaction. If we got a straight line with a natural log, it would be a first order reaction. We can see that's not a straight line though, which means that this is indeed a second order reaction. So there's our rate law right there. And then we could find our rate constant, our k value, just by using the integrated rate law. And so I just use our values at the time 0, and then after 100 seconds. You can use any of those other 3 points. It doesn't matter. You get the same k. And so when we do this then, we get a value of 0.52. Now let's talk units. We are subtracting molar up there, so those do not cancel out, and then we've got seconds on the bottom. Molarity is also on the bottom, which means that our units in this case is molarity inverse times seconds inverse. And there we go. That is the rate constant for this particular reaction. We could go and we could use that to figure out how much of NO2 is left after 1,000 seconds or how much is left after 1.5 seconds. We could use that since it's constant to find anything we need.